Hello. So today we are going to cover the various start to cover various kinds of mechanical components. Because you may need to study some kind of component uh, in your project, or in the future you may uh, need to have mechanical design of some components. So I will be briefly introducing how to what to worry about when you are designing those components. So even the textbook has a order of chapters. It doesn't matter which component, what's the order of learning those components, because they are very independent to they're independent, and when you put components together, of course, they may have reaction between components. Let me start to talk about. I think I mentioned a little bit about gears last time. So then I think we can talk about gears. Okay. So usually in like about the when you learn about the kinematics or dynamics or some other design courses about mechanism, you may be learning about various kinds of gears. Those are their names. If you, especially for Taiwanese, you may not know what their English name. So face to face is spur gear, and when the teeth has a like a helical angle, like a twisting angle, it's called helical gear. And battle gear looks like an umbrella. In Chinese, we call it umbrella gear, but the English is battle gear. So they are in the cone shape. The teeth are on the surface of the cone, and they are straight teeth along the uh, direction of the cone. You can have the most complex gear you can design would be bevel gear with helical teeth. Then it's very complex, especially for how to manufacture it. It's like you are manufacturing like a three-dimensional fan, and this is a worm gear. Looks like a worm. Okay, so there are some technical terms for the T, just as a reminder for you to know what I'm going to talk about later on. So for spur gear, this is one tooth, and somewhere in the middle there is a like a imaginary circle. Okay, you don't see it. It's somewhere right there. So it's called a pitch circle, and it's usually design with certain pitch circle first, then you design the proper profile of the teeth based on the pitch circle. And most of the time, for many gear calculations, we will draw pitch circles of the gear. And like this. Okay? So when you see two gears making with each other, the large one is called a gear, the small one is called a pin. In Chinese, we just call it big gear and small gear, but in English, it's a gear and pin. When we draw a picture like this, the circle is representing the pitch circle, and pitch circles are tangent to each other. Okay. Next is circular pitch. So it's an arc length from one edge of the gear of the tooth, from one edge to the other edge, to the same edge as the neighboring tooth, and the arc length is called circular pitch. So from there, then you know circular pitch equals to the entire parameter divided by number of teeth. Okay, we will see the equation later on. And the upper part of the teeth is called addendum. The lower part is called addendum. And upper part right here, the face is called the face. And then the lower part is called flank. Okay? And the face has a width, so it's called face width. And for later on, some of the calculation, usually the length right here, the width right there is labeled as F. Okay? What else? That's pretty much what we need to know for this slide. Now, there are many equations. So, pitch diameter basically is this diameter. Okay? So this is a small d, and circular pitch is a small p. So from what we just mentioned earlier, small p, the circular pitch, equals to the parameter, which is pi small d, divided by number of teeth. Okay, so that's definitely the easiest equation that you can memorize. Now, we now will define a value called diametral pitch. Diametral pitch is the capitalized P. Capital, the big P. So it has a relationship with a small p, like this. Small p times the big P equals to pi. So diametral pitch is number of teeth over diameter. So it's like a per unit diameter, per unit parameter, a diameter, how much teeth you have. Okay. So it's not an integer. Yeah? And if you reverse the equation, it's called module. Okay, module is the inverse of capitalized P. Okay, so those are the basic equations for P. You probably have learned this already. In that probably more than one lecture in the past. Okay. I want to move on to pressure pressure line. The pressure line. So let me see which is a better drawing. This one is a better drawing. This is, pay attention to this one. The circle that is tangent to the neighboring circle, the conjugating circle, are the pitch circles, right? Now, the teeth is supposed to be built somewhere right here. This one is somewhere like this. There's a circle called base circle. Base circle is like the base of the teeth of the tooth. Okay? So it's like the root of the tooth, and the pitch circle is at the middle, right? And you are not supposed to have a teeth, a tooth that is too long. Otherwise, you may have collision with the base circle on the other side. Okay, so you have, this is base circle, and this is your pitch circle, right? So you're supposed to have the teeth profile like this, but this cannot be too tall, otherwise you will hit the base on the other side. Okay? And when you have the teeth profile, let me draw the teeth profile on the other side. So this one is the base circle. So it's like this. I should draw on this. This is the base circle. Okay. Okay, this is one teeth on the lower side, one tooth on the lower side, and then the base circle on the top is this one. Oh no, this is not a. Sorry. The tooth should be grown based on the dedendum circle. The base circle is the base circle about the pressure angle. So I was wrong. The tooth should be grown within this range. So from the dedendum circle is like here. And then based on the drawing, it's actually up to there because this is the addendum circle. Yeah, addendum circle. So the tooth is like this. Okay. So from the dedendum circle, this word dedendum circle, up to addendum circle. Okay? And this is the dedendum circle on the other side, so the very top of the tooth won't be colliding with the other side of the ear. And right here, there is a straight line, pressure line right there. That's representing the contact position between the mating tooth, the mating teeth. So let me draw the mating teeth on the other side. So it should be looking like this. It's very difficult to draw. It's- yeah, yeah, okay. So they have a tangent contact right there. And the tooth profile is designed based on the involute curve. Mathematically, it will be always perpendicular to the pressure line. So this is pressure line. And you have so-called the pressure angle here, pressure angle. And this involute curve is supposed to be perpendicular to the pressure line all the time. So when the gear rotates, the tooth moves, rotates to the other position. So the since this involute curve has to be perpendicular to the pressure line. So when your tooth is up to some other position, for example, the tooth on this side. Okay. So right here, you can see the involute line is still the perpendicular line is still perpendicular to the pressure line. However, if you stand on the teeth, this involute line actually change its angle, right? If you are standing on top of this teeth, the involute line is somewhere on the side. But if you stand on here, the involute line is like rolling up. So the involute line the involute curve defines the shape of the gear tooth. Okay, so why is it designed in this way? So it's designed in this way so that no matter which angle your gear is, the contact between the making tooth is always along this pressure line. So whatever force that you are generating on the other side, that will be perpendicular. That will be passing along this pressure line. So mathematically, it's easier to handle. So you would know you have a pressure angle, and whatever force on the other side, that will be moving along this phi right there. Do we really have to have a gear design in such a way? Can we have varying pressure angle? Actually, mathematically, you can do it. So there are actually researchers try to design special gears with a special tooth profile, like Professor Xu Guanlun in NTU. He has he showed me some of his previous designs. But in this course, we don't work on that. We are not a course about gear design. So anyway, that's pressure line, and the pressure line is tangent to the base circle, right here, tangent. So the contact point between two mating teeth lies on this pressure line. Okay, so when two mating teeth first contact with each other, the contact point stays on the pressure line, and then as the two move like this, that contact point pass along this pressure line. Okay. Yep. actually shows a pretty good drawing from here, better than what I've drawn. Here, you can see that there's a point A and point B. It's like the very left edge of the contact and the right edge of the contact. Okay? So there will be various kinds of calculations about pitch and pitch along different directions. Right? Earlier we mentioned you have two spur gears mating with each other. The big one is called gear, small one is called pinion. Now, when you have a linear gear, it's called a rack. Okay, what is a rack? It's basically a gear with a radius of infinite large radius. That is a linear gear, and that is called a rack. So often we will say rack and pinion. Why do we say rack and pinion? Because rack is a gear with radius equals to infinity, so it's the large one. So the mating gear is a smaller one. So the small one is called a pinion. So you often heard rack and pinion, the term rack and pinion. Okay, so you can just treat it like a spur gear, but it has super large radius. Okay, and since it's becoming a linear direction, so the circular pitch now is basically the length from one edge of the tube to the other one. It's a linear line, not an arc length anymore. And since you for rack, the tooth now is following this straight lines. So you can also study the pitch along this direction. And this direction is basically following the pressure line, right? And pressure line basically is tangent to the base circle, right? So that's why if you study the pitch along this direction, it's also called the base pitch. And the difference between the base pitch and the circular pitch is that there is a cosine phi relationship right there. Okay? Now, for the I need to go to the helical gear. Here, my slide, the order of the slides, a little bit weird. Now, since we are introducing pitch study in different direction, for helical gear, basically, it looks like a spur gear if you visualize it along this helical angle. So the section BB is like when you are observing the tooth profile along this helical angle. Okay, so right here, this is the helical angle. Doesn't say so helical angle. Okay, and when you observe the tooth along this direction from the side, you will see this section BB, and then right here, this is the pressure. But the pressure angle will be different when you observe along this direction or this direction. So they separate them into two terms. One is with the the subscript n. So whenever you see subscript n, it's called normal. It means normal. And when you see subscript t, it means transverse. Okay. And when you see subscript x, for here it means the axial direction along the axis. Axial. Okay. So now you have pitches measured along three different directions to describe the tooth shape in this three-dimensional space. So from the profile right here, it's like this. Okay. So it's like a addendum, dedendum, addendum, dedendum, like this. Okay. So if you view in this way and you try to take a look at, for example, study a point here to here, the same point. That would be the pitch along this direction, in this observation direction. And since when we observe in this way along the helical angle, the profile looks like a spur gear. So we call this like a normal direction. Okay, so the pitch along this particular helical direction, we have this normal term right there. So normal pitch is right here. Normal circular pitch. It's the same as what the arrow that I have drawn right there. And if you observe along this, if you observe from the side, looking up, from the bottom looking up, and your eyeball is looking up along this central axis of the gear, then you also see this profile. So it's like right here, like this is up, and this is down, right? So this will be up here. So if you observe from this side, so you will see like this, right? And the pitch along this direction. So if you pick up a point here and then measure the pitch along this observation direction, it's like you are putting the gear like a you're observing the gear on the side. So whenever you are visualizing or analyzing something from the side, it's like a transverse direction. Okay, like a horizontal, and you're staying horizontal to the general axis. Okay, so it's called a transverse pitch circle. Transverse pitch, and when you have if you are able to study the tooth on this weird side, okay, you actually see if the tooth is very large, if the gear is very, you should say long. So if you have a helical gear like this, okay, let me draw a simple version. Okay? And then, if I draw the profile like this, if this is Okay? So I didn't draw the other line. From this normal direction, you see a tooth. From the transverse direction, you also see tooth profile like this. Ah, from the transverse version, it looks like this. Not very good drawing. Okay, you also see profile like this. If you observe from this side, but if you observe from this side, this is the dedendum. This is dedendum. This is addendum, right? So if you observe on this side, so this is addendum again. So it's like this. Uh, If you view from this side, your eyeball is now perpendicular to the central axis. You actually can see a periodic profile. So you can actually measure the pitch as well. So it's called the px, the pitch along the axial direction. Okay, so that's why right here is giving you how to compute Pn, Pt, and Px. Be aware that we have learned small p times big P equals to pi. This is only valid for normal. Why is that? Because the profile of the helical gear is just like the spur gear when you are observing the profile along this normal direction. So whatever equation you are having for the spur gear should be valid for the measurement along this normal direction. Okay, so that's why the spur gear calculation is utilized for the calculation along this normal direction. Okay, so that's something to remind you. And let me continue. I would like to talk about the bevel gear. Okay, let me use this one. So for the bevel gear, it's how do you study the tooth profile? So this is where the teeth are mating with each other, and the teeth has been built along the cone shape. How do you study? How can you use whatever gear equations that you had earlier? So right here, there is a virtual gear for the purpose of calculation. It's like whenever the two the teeth are mating with each other for the bevel gears, right here the profile shape still looks like a spur gear. Okay, so you can imagine there is actually a virtual spur gear right here. It's like central axis is right here, and there is another virtual gear right here. Central axis is right here. Okay, so it's just like how two spur gears are mating with each other with a virtual number of teeth, and then after a certain calculation, you apply the profile on a cone. So that's why you see this virtual number of teeth. Okay, virtual Spurky. The virtual Spurky actually looks like that. Okay. So these are the information for you to know. Because if you are in the future designing for gears, you should know the geometrical relationship between different kinds of gear components. But for us, once we understand the geometrical information of gears, next part we worry about is the force and stress. So we now would like to move on to the next presentation, next lecture slide, where we talk about the loads. We can first talk about this one. So this is the force diagram, free body diagram between spur gears, gear and pinion. Simple. So let's say I have a motor that is driving the pinion. Okay, so the motor has a torque driving the pinion. So assuming no energy loss, so whatever power that I put into this particular small gear will be 100% transferred to the other side. So I can then compute for, like for example, the rotation speed. But what can we also study? Which is the forces that is applied to the teeth. So when we have a drawing like this, we are actually having the drawings of the pitch circles and pressure angle. So we know the force passing between both sides that must be lying on the pressure angle. So I know if I have a tooth right here, okay, so the force that was being applied from the pinion to the gear has to be going this way. And since I am rotating the pinion clockwise, so it's like, the other side is resisting my rotation, so definitely I'm pushing it. So if I stay on the big gear, I know there is a force pushing me along this pressure angle. So this is how you determine the direction of the force. So if one day we reverse the rotation, then the pressure angle now is following this pressure line. If we reverse the rotation, then we are then pushing, the pinion is pushing the gear, this time from the right over corner. So the force will be pushing like this. Okay, so the way to observe the direction of the force needs to be based on the direction, orientation of the gears. So once you know there's a force being pushed, so you have a pushing force from the pinion to the gear. So the reaction, there will be exact same reaction force. So the gear will have the same force but different direction pushing back. So this is the reaction force. Okay? And if we observe individual gear, in order to have balance of the forces on the shaft, you have to have because exact same size of the force but different direction. So there would be a reaction force on the shaft. So that's how the force is balanced. But when you have two forces that are having the exact same amplitude but different along different line, it's a couple. So the force couple will generate torque. So the torque generated by the force couple has to be balanced. So there will be a balancing torque. Okay, so this balancing torque will be balanced with the torque generated by the force couple. Okay, so actually, when you have gear, the gear will generate the mating of the gear and the operation of the gear and pinion will not only apply a force to the teeth, but also generate a torque to the gear set. So that torque will be applied to the shaft. So if you are studying for the shaft design, you have to know on the every position where you install a gear, there will be generation of torque. Okay, so the gear is actually twisting the shaft. So if you have multiple shafts, each of them are being mated with different sets of gears somewhere. So each gear will be having some kind of torque. So the shaft will be twisted in a certain way. Okay. So that will, if we go back to our shaft design at the very beginning of the lecture, this part of the lecture is very related to shaft design lectures. The only thing is, in our problem solving, we're only solving very simple problems. But in reality, the entire shaft is carrying multiple kinds of loads. Sometimes distributed load, sometimes twist and complicated. Okay, anyway, that's for the gear side. Similarly, for the pinion side, you also have a reaction torque that is used to balance. That is balancing the torque generated by the force couple. Okay? So that's for spur. You can separate the angular force into two components: the vertical one and horizontal one. The transverse component is more important for teeth design, for tooth design. So let's say there's a tooth. We care more about the transverse one if when we are studying for the null condition for the tooth. Because the vertical one, which is along the radial direction, R represents radial, and T represents transverse. Okay? The transverse load will bend the tooth. The radial force just push the tooth toward the center. Bending will cause failure to the teeth, not the pushing force. So when we are studying for the stress and failure of the teeth, we care more about the transverse force. Okay. That's for spur gear. Yeah, this is like a more complex problem when you have three gears mating with each other, and you can see if you are studying for the largest gear, number 3 right there, you will see there are some forces coming from the left, there are some forces coming from the bottom, and you won't know how much force that you have at the shaft of the gear 3. Then you need to define some reaction forces like this, and then compute for balance of force. Okay. So next week we will be continuing on more gear designs. Gear is the biggest chapter in this textbook. Okay. So next time we will talk more about gears. Then I will move on to some other components. Okay. Before you go, let's do the roll call. So please make sure you do that. Then that's it for today. If you have questions about your project, you can come here.